Good morning, everybody. Today I'm going to show you the result of a work in which pure orange juice was investigated as a feedstocks for the production of hydrochars. The depletion of fossil fuel and corresponding environmental issues have sparked the intense development of sustainable and high-performance energy storage technologies to meet global needs. Of these technologies, supercapacitors show great promise for application in portable devices, stationary energy storage systems, and electric vehicles due to merits including high specific power, long cycle life, and ultra-fast charge discharge. In general, two types of storage mechanism exist for supercapacitors, in which one involves electrical double-layer capacitors as represented by carbon-based materials, and these depend on physical electrostatic attraction between ions and electrode surface, whereas the other is based on the pseudocapacitance principle, in which energy storage is generated through fast and reversible redox reactions or Faraday charge transfer reactions. Regardless of the mechanism, however, electrode materials in supercapacitors play a significant role in determining electrochemical performance. Because of this, tremendous efforts are being made to develop novel electrode materials for high-performance supercapacitors to meet the increasing needs of emerging technologies. Among these novel electrode materials, carbon materials have attracted intense attention due to unique properties such as functional surface, cost-effective nature, superior electronic conductivity, and excellent cycling stability. Despite this, the widespread development of functional carbonaceous materials is limited by corresponding fossil fuel-based precursors such as coal or cinder, and inferior rate capabilities as well as complex and energy-intensive synthesis process. To address these issues, biomasses have recently gained attention as viable feedstocks in the synthesis of carbon materials for supercapacitor electrode due to their renewable nature, productivity, and environmentally friendly characteristics. In addition, these biomass-derived carbonaceous materials can be produced from various sources in daily life, such as flax, lignin, peanut shells, and unlike other carbon materials, biomass-derived carbon materials can readily inherit the unique structure, defect, and chemical composition of biomass precursors during carbonization, allowing resulting biomass-derived carbon materials and corresponding composite to deliver high capacitance, improved array stability, and excellent cycling performance at low cost in high-performance supercapacitors. Thermal conversion is nowadays a strongly investigated route to convert natural precursors in carbon nanomaterials to be used in supercapacitor electrodes. The decomposition of biomass is often obtained by pyrolysis in the absence of oxygen, giving rise to the preferential production of biochar by oil or gases, depending on final temperature and thermal environment. In recent years, wet pyrolysis, also called hydrothermal carbonization, has gained increasing interest due to the relative simplicity of the process, including the fact that biomass doesn't need to be dried before treatment, avoiding the energy consumption due to the drying process. In fact, water containing the natural precursors is part of the medium in which hydrothermal reactions take place. And the solid product of hydrothermal carbonization is named hydrochar to distinguish it from biochar obtained by pyrolysis. With respect to dry pyrolysis, hydrothermal carbonization has different advantages, such as lower working temperatures, lower ash production, and a higher density of functional groups containing oxygen in the solid product. In a hydrothermal carbonization, biomass is subjected to autogenous pressure in a confined environment in the presence of subcritical water, that is, water in the liquid phase at temperatures between 100 and 300 Celsius degrees. Orange peel and orange pomace were investigated as feedstocks for the production of hydrochars. On the one hand, Erdogan and co-workers studied the hydrochars and the aqueous phase produced by the hydrothermal carbonization of orange pomace at various temperature and residence times. On the other hand, Fernandez and co-workers activated hydrochars obtained by the hydrothermal carbonization of orange peels to assess them as absorbent of contaminants. Physical and chemical activation resulted in a specific surface area in 300-600 square meter per gram range. In a later work, orange peel waste was treated by hydrothermal carbonization and then mixed with lignin, cellulose, and hemicellulose to modify the quantity and properties of resulting hydrochar. It was shown that cellulose and hemicellulose increased the density of microsphere on the surface of hydrochars, and a maximum specific surface area of about 27 square meter per gram was found for lignin added hydrochar. To the best of our knowledge, the hydrothermal carbonization of orange juice was performed only to synthesize carbon quantum dots. In this work, I present to you a study in which pure orange juice was hydrothermally carbonized and the resulting hydrochar was filtered and washed and activated by potassium hydroxide in nitrogen atmosphere at 800 Celsius degrees. The hydrochar obtained from orange juice was in form of microspheres with a well-defined surface as shown in the SEM and TEM images. Statistical analysis of the size of the spheres gave the histogram shown in the slide, from which we calculated an average value and a standard deviation of about 5 and 1 micron respectively. The X-ray spectroscopy analysis show that the carbonization process gave rise to a material made mainly of carbon and oxygen with some nitrogen. Also, the spectrum show no traces of other impurities. And the X-ray diffraction indicates that the microspheres contain partially graphitized particles. The width of the 200 peak, centered at about 22 degrees, is very likely due to a wide range of independent distances, higher with respect to graphite, in which the peak is centered at about 27 degrees. The partially graphitic character of microspheres is confirmed by the Raman spectrum. The presence of the defect activating the peak, although showing a large width compared to the spectrum of defected graphite, is indicative of the presence of aromatic rings. In graphitic materials, the intensity ratio of D and G peaks is used to estimate the degree of crystallinity, but in the present case, the intensity of D and G peak have to be intended as the peak heights, and this is the more reasonable choice because in hydrochars obtained by the carbonization of biomass, the broadening of the D peak is due to contributions coming from distorted clusters with ring orders other than 6. It has been shown that in these materials the D width can be associated to aromatic breathing mode. Therefore, the information about less distorted rings is contained in the D height rather than its area. The surface of the microspheres is covered by functionalities as demonstrated by the infrared spectrum. Peaks can be interpreted as being due to the presence of hydroxyl, carboxyl, carbonyl, quinone, and ester species, and the porosity of hydrochar microspheres was studied by nitrogen adsorption-desorption experiment, and before activation, the specific surface area was 12 square meter per gram. The morphology of microspheres was strongly affected by potassium hydroxide activation. As we can observe from TEM images after activation, the spherical shape was retained with an induced porosity clearly visible in the peripheral areas. And the elemental analysis showed that after activation, the weight percent of carbon, hydrogen, and nitrogen is 76.36, 0.75, and 30.67 respectively. Therefore, activation doesn't cause a significant change in the carbon content. On the contrary, the final hydrogen content is very low and the nitrogen percentage increases significantly. Considering the measured ash content, we calculated an oxygen weight percent of 9 in the activated sample. The high nitrogen content could be important in the view of a possible use of the material in supercapacitor electrodes. In fact, it has been shown that in porous carbon materials derived from biomass, oxidation stability and electrochemical performance in the perspective of their use in supercapacitor electrodes. The Raman spectra of the non-activated and activated sample show an increase in the DG intensity ratio from 0.83 to 1.17. In graphitic materials, an increase in the ratio is usually interpreted as being due to an increased density of defect. However, in the case of chars, which are made of small clusters containing aromatic rings, the interpretation is opposite. It has been shown by Ferrari and Robertson that for crystallites with a lateral size lower than 20 angstrom, an increase in the DG intensity ratio is related to an improved level of order. In fact, for small crystallites, a high density of defect can destroy aromatic rings, lowering the intensity of the breathing mode, while the G peak doesn't suffer a decrease of the same extent, being related to the carbon-carbon stretching mode. In the case of chars obtained by the carbonization of biomass, the clusters containing distorted carbon rings with different ring orders have sizes below 20 angstrom. Therefore, the DG intensity ratio increase very likely indicate an increased structural order generated by activation rather than an increased disorder. As a matter of fact, treatment with potassium hydroxide at 800 Celsius degrees in a nitrogen atmosphere cannot be simply considered as an activation, but rather a graphitization activation. And X-ray diffraction measurement before and after graphitization activation showed some evidence of enhanced graphitization after the potassium hydroxide treatment. Our findings are reasonable because hydrochars have a low degree of graphitization and treatment at 800 Celsius degrees in the presence of potassium hydroxide causes the destruction of part of the material, but very likely the remaining carbon materials has a graphitization degree higher with respect to starting microspheres, and the specific surface area calculated from a nitrogen adsorption-desorption experiment is 70-25 square meter per gram, which is not the higher range of the specific surface areas observed in activated hydrochars, but is noticeably higher with respect to the hydrochars obtained by the hydrothermal carbonization of orange peel. However, the specific surface area value is not the only aspect to be considered to assess porous carbon materials as potential electrode in supercapacitors. A crucial rule is played by the pore size distribution, which must exhibit both micropores to maximize the amount of charge and then the energy density, and mesopores to facilitate the flux of electrolyte ions, increasing the power density. The activated carbon microspheres obtained in this work have a high density of micropores, as demonstrated by the pore size distribution in Figure B, and a mesopore structure clearly observed in the same curve, which give rise to the typical hysteresis in the isotherm in Figure A. To conclude, orange juice is not considered to be a waste, and this is probably the reason why it's not being considered as a potential feedstock for hydrochar production. However, low quality oranges don't have market in southern Italy, and their cost can be roughly estimated to be a few tens of euros per ton. Given the high quality of the final product in terms of specific surface area, pore size distribution, and nitrogen content, it can be concluded that the production of porous carbon by the hydrothermal carbonization of orange juice, followed by activation by potassium hydroxide, appear to be a greatly interesting route to develop efficient and low-cost supercapacitor electrodes. Finally, I would like to thank Andrea Scarcello and Lorenzo Caputi for having contributed to the realization of this work, and I gratefully acknowledge the University of Calabria and the Community Energy Storage Project for supporting this research. Thanks for your kind attention.